Okay, before we start things off, I want to think about a matrix, a tall matrix. Suppose I've got a really tall matrix, and I've got, this is M by N, right? And I'm thinking of these, um, each of these columns, the N columns, I'm thinking is a different dimension of our data, right? So I'm actually thinking of the data row-wise when I do that, right? So each row represents like dimension 1. Oh, I'm sorry. Let me say that differently. Each column represents a dimension, and each row vector is is kind of gluing which pieces of which dimension go with which together, right? So if I were to find the mean would be taken down, and I would have a row, and this would be a vector in Rn. Okay, and so the idea here is I might be interested in how the columns covary with each other. And so I may, for example, take a look at the first column of M points and compute the covariance between it and the second column. Okay, and then I could put that in another matrix in, say, the 1, 2 position. So that would be like the covariance of S with 1 and 2, right? Just to fill this in, we could have the actual variance vector in the 1, 1 position, because that's the covariance of a vector with itself. And then similarly, we could compute how the first column covaries with the third, and then we could compute that value and put it here. Okay, and so on. And then how many do I have? 1 and N I could put there. Good. Now similarly, I could take column 2 and compare it to column 1. By the way, is S12 squared the same thing as S21 squared? Yes, right, because of the definition of the covariance. Remember that that's equal to, if this is x and y, right, this would be x minus x bar squared. Oops, that's the variance, times y minus y bar. And then if I flip those, does it matter? I could put the y first, right? And it doesn't matter. And so this would be the same thing as this. But I could write it as S21 squared if I want. But I want to emphasize that this value is the same as that value, right? Good. And then I could compute S22 squared. That's the variance of the second one. And along the diagonal then, I would just have the variance of each column. Okay, and then the off diagonals, I would have the covariance between column I and column J, right? And so this matrix right here, this is an n by n matrix, n by n and symmetric. By the way, are symmetric matrices nice in terms of eigenvectors? Yes. So we want to kind of mention that in passing, that the covariance, this is called the covariance matrix. Okay, so if you have more than one, or 2 columns of data, right, you can compute a covariance matrix. In fact, if you put in 2 vectors into MATLAB and I think in Python, they'll go ahead and compute a covariance matrix instead of just giving you the variant, how the 2 covary. So yeah, so do you see how this is now working with our definition? So in terms of our definition, in the notes, we see that Sij squared, the ijth entry of the covariance matrix, is equal to, I'm going to change the notation a little bit just to match my picture up here. I should have put P instead of M there, I guess. Oh well. That'll be M minus 1 in our case, times the sum. and I'm going to be counting down the 1 to m, and this is going to be the kth column. Oh, I'm counting down the kth row. Let's see. I guess I better be careful with my I and j, right? So I and j means I'm taking column I with column j, right? And then I'm going to be summing down in the row. And so this is going to be the ith column with the jth column. Good. And then I'm going to be summing the row values. Excellent. All right. And this, by the way, is assuming what? That I've mean subtracted NRN. If I have not mean subtracted, then I would have to subtract the mean of each of these, right? The mean of the column. Did I say that? Well, we'll see how that works in just a sec. Okay, so this is the mean is NRN, because we're thinking about this as being m points in Rn. Very good. All right, and so just as a point of reference here, you can actually compute this in one single computation using some linear algebra. And so we'll define the covariance matrix as C, and that'll be 1 over, I'm going to switch notation on us. Let's say X is P by N, mean subtracted. And again, mean subtracted means the mean is in Rn. Okay. This ought to be 1 over P minus 1 X transpose X. So if X is P by N, this is N by P. This is P by N. So the result is your N by N covariance matrix. What does the covariance matrix represent? It represents how it represents how the ith and jth columns of X covary. Okay, how the ith and jth columns of X covary. Good. And let's see. I guess while I'm here, let's go ahead and take a look to see what the command is in the 3 languages. Our MATLAB. If I have X already written out as a P by N array, then C is just going to be the covariance of X. In Python, C is going to be, C is NP dot, that's the NumPy, covariance. It's interesting, Python has this kind of reversed. I'm going to have to take X dot T, the transpose, to get it right. And then I'm also going to have to say bias equals false. Bias is the term that you're dividing by here, and this flag right here is saying whether you want to divide by P or P minus 1. So taking bias equals false, I'm pretty sure that means that you're dividing by P minus 1. You'll have to double check. Good. Now I just wanted to run through a couple of exercises with you just to make sure that you've got a good start on them. Okay, so let's get a start on 4a maybe. 4a says let X be a vector of data. So this is scalar data, so X is in like Rn with variance Sx squared, and let A and B be scalars. So in part A we want to show that the variance of Ax is equal to A squared times the variance of X. Okay, so let's see. what is that in terms of our definition? Right, that's 1 over, did I say how long those vectors were? I did not, so I guess we'll just use m for the length of the vector. I equals 1 to m. And then we're going to take a times our xi, right, minus ax bar, the mean of ax, right, squared. And now in 3a, we show that the mean of a times x, how am I going to write that? The mean of a times the vector x is a times x bar. That's pretty straightforward to show. So in that case, I can replace my a times x with a big bar by, what am I going to do? Can you guess? A times x bar squared. And now, of course, I've got the common a there that I can factor out. So this is just some pretty straightforward algebra here. Factor out the a, and it's actually an a squared, right? Now we can take the a squared all the way out, and we're done. Okay, oh, so I guess I did all of 4a for you. Okay. So a similar game can be played in 5 and 6 and 7, and yeah. 5, 6, and 7 kind of go in the same way. Take a look at their definitions, or the definition of what you're working with, and see if you can just factor the constants out, and I think things will work out for you. Good. Okay, that takes us to the end of page 22 in what we're calling chapter 2, which is the statistics chapter so far. It starts at page 17 and goes to page 22. Good. That's it for today. Next time when we get together, we'll be talking about something called the best basis for a data set. So that's why we needed a little bit of statistics, is the best basis can be interpreted statistically in a nice way. Okay, see you then.